There is a moment in the wild places of this earth when the animal brain wakes up. Not the thinking brain, not the part of you that makes shopping lists and checks notifications and plans for next weekend. The older part, the part that has been there for hundreds of thousands of years, coiled quietly beneath the surface of modern life, waiting. It wakes up when the ground shifts beneath your feet. It wakes up when something moves in the trees at the edge of your vision and you cannot immediately identify what it was. It wakes up when you realize, with a clarity that no amount of comfortable living can fully replicate, that you are not at the top of the situation, that something else might be. That your body, this improbable collection of soft tissue and fragile bones that you carry through air-conditioned rooms and carpeted offices, and well-lit supermarkets without ever once thinking about how catastrophically vulnerable it actually is, might be relevant to the survival calculations of another creature entirely. And in that moment, everything changes. The world comes into focus in a way it almost never does. Colors become sharper, sound becomes layered, the distance between where you are standing and where you need to be becomes the most important measurement in the universe. You are no longer a person, you are an animal, and the question the universe is asking you is very simple and very old, and in some ways the only question that has ever really mattered. Are you fast enough? Are you smart enough? Are you paying enough attention? Subscribe right now if you want to understand what survival actually looks like, not the television version, not the staged version, but the real version, the version that has been playing out in the wild places of this earth for longer than our species has existed. We are going all the way in. Let us start with water, because water seems like it should be the safe thing. Water is where you go to drink, where you go to cool down, where you go in the mind of a creature that evolved on the African savanna and learned early that water meant life. And water does mean life. Water means life for everything, including the things that eat you. The drinking holes of the Kruger National Park in South Africa are among the most intensely observed patches of ground on the planet, photographed and filmed and watched by researchers and tourists and wildlife cameramen with a dedication that borders on the obsessive. And the reason they are so obsessively watched is the same reason they are so extraordinarily dangerous for every animal that approaches them. A drinking hole is a place where the normal rules of the savanna are suspended, where prey animals that would never normally allow themselves to be exposed in open ground are forced to expose themselves because the alternative is death by dehydration. And predators know this. They have always known this. A leopard that positions itself in the fever trees above a drinking hole in the late afternoon is not there by accident. It has been watching. It is calculated, with the kind of intelligence that gets dismissed as mere instinct because it does not come with a language we recognize as language, where the impala come to drink, and at what time and from which direction and how close to the water's edge they allow themselves to approach. It has considered the wind direction, which matters enormously, because an impala's nose is a more sophisticated threat detection system than anything our best engineers have ever built, capable of identifying the specific chemical signature of a leopard at a distance of several hundred meters. The leopard positions itself downwind, always, not because someone taught it the concept of wind direction and its relationship to scent dispersal. Because the ones who did not do this did not eat as often, and the ones who did not eat as often did not survive as consistently, and the ones who did not survive as consistently did not pass on their approach to drinking holes. This is what 30 million years of coevolution looks like. A leopard in a tree that knows things about the animal it is hunting that the animal being hunted does not know about itself. But the impala has been in this situation before. Not this individual impala necessarily, though a mature impala has survived every previous encounter with every previous predator, and that fact alone represents a curriculum. The impala as a species has been navigating drinking holes and ambush predators for an evolutionary history that rivals the leopard's in length, and exceeds it in the specific intelligence of threat detection. Because while the leopard has to be smart about hunting, the impala has to be smart about everything. An impala does not get to specialize. A leopard is hunting you. A hyena is hunting you. A wild dog is hunting you. A cheetah is hunting you. A lion is hunting you. A crocodile is hunting you, specifically at the drinking hole, in a form of ambush predation that is so ancient and so effective that crocodiles have been doing it in essentially the same way since before the dinosaurs. Every threat requires a different response. Every threat has a different profile, a different speed, a different pattern of attack, a different most dangerous moment in its approach. The impala's brain is managing a threat matrix of extraordinary complexity every moment of every day. And it does this while also finding food and navigating social hierarchies, and reproducing and caring for young, and managing the basic biological maintenance of a body that is already running at the edge of its physiological limits just to exist in the environment it exists in. So the impala approaches the water carefully. It approaches with its head up, not down. It scans the tree line, the reed beds, the surface of the water itself. It waits. An impala at a drinking hole will wait for long minutes before committing to the approach to the water's edge, testing the air, watching the other animals. And this is the thing about the other animals, they matter. In the ecosystem logic of the African savanna, the presence of certain animals near water is information. Oxpeckers on a hippo's back are not concerning. A group of vervet monkeys suddenly moving toward the upper canopy for no apparent reason is very concerning. A flock of birds erupting from the reeds in a single panicked mass is the equivalent of a fire alarm. Every species at the drinking hole is simultaneously managing its own survival, and as a byproduct of that management, generating information about the current threat level that every other species present can read. This is what ecologists call the information landscape of the savanna, and it is as sophisticated as any human communication system and considerably more reliable, because it is not based on language that can be misunderstood or manipulated or politicized. It is based on behavior, on the involuntary body language of genuine fear, which cannot be faked because it is generated by systems that are not under conscious control. When vervet monkeys produce their specific alarm call for a ground predator versus their specific alarm call for an aerial predator, they are not deciding to communicate this information. They are responding to a threat, and the response happens to carry information that other species, through long proximity and selection pressure, have learned to decode. The impala hears the vervet monkey ground predator alarm call, and its body responds before its brain has processed the sound. Because in the time it takes to process a sound, a lion can cover 12 meters. The drinking hole, then, is not a simple thing. It is a node in a network of attention and information and calculation that involves dozens of species simultaneously, each one managing its own survival with a sophistication that we have barely begun to understand, let alone document. And in the middle of all this, a leopard is lying in a fever tree, watching, waiting, calculating, with the patience of a creature that knows it cannot afford to fail because failing often enough means starvation. Let me take you to a different kind of water. Let me take you to the Amazon. The Amazon River system is, by every measure we have to apply, one of the most extreme environments for survival that exists anywhere on this planet. It is not extreme in the way that a desert is extreme, through the absence of things, through heat and dryness and the brutal simplicity of a landscape that offers very little. The Amazon is extreme in the opposite direction. It is extreme through presence, through abundance. Through the sheer density and complexity and relentlessness of life, packed into every cubic meter of water and every square meter of forest floor, and every layer of canopy from the dark and humid understory to the sun-blasted emergent trees that break above the main canopy and feel the direct force of the equatorial sun in a way that nothing below them ever does. In a system this dense with life, the survival mathematics are extraordinary because everything in the Amazon is eating something else in the Amazon, every niche is filled, every energy source is exploited, every weakness is found and leveraged. The result is an arms race of evolutionary adaptation that has been running continuously for longer than the Amazon basin as we know it has existed. Because the forest preceded the river, the ancient Gondwana forest that preceded the elevation of the Andes and the creation of the westward drainage that became the Amazon, and the evolutionary histories of many Amazon species are older than the river that now defines the basin. The black caiman is the largest predator in the Amazon River system and one of the largest reptiles in the world. Males can reach 5 meters in length and weigh close to 1,000 kilograms. They have been in this river for a very long time, in forms recognizable as the ancestor of the current species, for millions of years. They are ambush hunters of extraordinary efficiency, capable of lying motionless at the surface of dark river water for hours, their bodies indistinguishable from floating logs in the murky light of the forest-shaded waterways, their eyes and nostrils barely breaking the surface. And then something comes to the water's edge, and then nothing wastes time. The strike of a black caiman is one of the fastest large animal movements in the natural world, not because caimans are fast swimmers, though they are fast enough, but because the attack uses an energy storage system that is almost mechanical in its efficiency. A caiman at rest is not burning energy maintaining muscle tone the way a mammalian predator is. Reptiles operate on a fundamentally different energetic model. The caiman at the water's edge is cold, in the physiological sense, running its body at a fraction of the metabolic rate of any mammal of equivalent size. And when the moment comes that stored energy, those muscles that have been waiting without the continuous drain of mammalian metabolism, can unload in a burst that produces forces that are, quite literally, among the strongest bite forces ever measured in a living animal. But the Amazon is not only the caiman's river. The giant river otter, which can reach 2 meters in length and is probably the most aggressively social apex predator in the Amazon system, shares the same waterways. Groups of giant river otters hunt cooperatively, herding fish in a coordination that has to be seen to be believed, because it looks organized in a way that suggests a level of social intelligence that mammal predators have developed in various forms across the animal kingdom. They are loud, these otters, extravagantly, almost comically loud for predators, their whistles and screams and growls bouncing off the forest walls as they work, and yet they are devastatingly effective. A family group of giant river otters can consume 40 kilograms of fish per day. They will challenge black caimans for fishing territory, not metaphorically, literally challenge them, mob them. The otter group surrounds the caiman, screaming at it, approaching from multiple angles simultaneously, taking advantage of the fact that the caiman, for all its ancient power, cannot effectively watch every direction at once, until the caiman backs down and finds a different part of the river. This tells you something important about survival in the Amazon. Size and power, while useful, are not the whole story. Social complexity, cooperative behavior, the ability to coordinate action with members of your group toward a shared goal, these are technologies of survival that can overcome physical advantages that seem insurmountable. The group of giant otters that mobs a caiman is doing something that requires trust, or whatever the otter equivalent of trust is, requires the ability to predict what your companion will do and to coordinate your own action with that prediction, requires a social bond strong enough that you will put your own body between a 5-meter crocodilian and your family member. That is not instinct in the dismissive sense. That is something that has to be built through lived experience within a family group, through the specific knowledge that accumulates when you hunt together day after day in the same stretch of river and learn each other's movements and tendencies and strengths. Now let me take you to a completely different scale of survival. Let me take you small. Because the survival battles that happen at the scale we cannot easily see are in many ways more extraordinary than anything happening among the megafauna, and understanding them changes how you look at everything else. The leafcutter ant colony in the Amazon basin is one of the most complex biological organizations on Earth. A mature colony can contain anywhere from 1 million to 8 million individuals, occupying an underground network of chambers and tunnels that can extend 15 meters below the surface and cover an area the size of a football pitch. The colony is not in any meaningful biological sense a collection of individuals. It is a superorganism. The individual ants are less like members of a society and more like cells in a body, each one specialized for a specific function, unable to survive alone for more than a very short time, but together constituting something that is one of the dominant ecological forces in the neotropical forest. The survival challenge that leafcutter ants have solved, and this is the genuinely extraordinary thing, is agriculture. Leafcutter ants do not eat the leaves they cut. This seems like the most important piece of information about them, and it is almost always either omitted or mentioned briefly without the weight it deserves. They cut leaves and carry them underground and feed them to a fungus. The fungus is their actual food source. The ants are farmers. They have been farming the same species of fungus, cultivating it, selecting it, protecting it from contamination, feeding it, harvesting it for approximately 50 million years, which means that leafcutter ants developed agriculture 50 million years before humans did. The implications of this are staggering if you follow them. 50 million years of continuous agricultural practice has produced a relationship between the ants and their fungus that is so deeply co-evolved that neither organism can survive without the other. The fungus has lost the ability to reproduce sexually, because it has been propagated vegetatively by the ants for so long that the sexual reproduction mechanisms have atrophied. The ants carry founding samples of the fungus in a special chamber in their bodies when a new queen leaves to found a new colony, because without the fungus the colony cannot eat, and without the colony the fungus cannot survive. They are locked together in a dependency so complete that they constitute together a single biological entity in some meaningful sense. And the threats to this system are existential in a way that makes the individual survival challenges of the savanna look simple by comparison. Because the fungus garden, the warm, humid, nutrient-rich underground space where the colony grows its food, is one of the most inviting environments imaginable for parasites and pathogens. A specific parasitic fungus, Escovopsis, has evolved specifically to attack and consume the leafcutter ant's cultivated fungus, and has been locked in its own evolutionary arms race with the ants and their crop for essentially as long as the agricultural system has existed. The ants' response to this threat is one of the most elaborate and sophisticated disease management systems in the biological world. Within the colony, there are specialized castes of ants whose function is what we would call sanitation and medicine. They patrol the fungus garden, removing infected material before it can spread, carrying dead ants and fungal waste to specific dump chambers that are maintained at a distance from the main colony. They apply with precision secretions from specialized glands containing antibiotic compounds produced by bacteria that live in symbiosis on the ants' bodies. another layer of biological partnership, bacteria that produce antibiotics that keep the fungal parasite in check, that have been living on leafcutter ants and producing these specific compounds for what appears to be tens of millions of years. The colony, the fungus, the antibiotic bacteria, the parasitic fungus. All of them locked in an evolutionary dance of survival that makes our most complex medical interventions look like something you could explain to a child. Let me go somewhere cold. Let me take you to the Arctic, because the survival challenges of extreme cold are different in kind from the challenges of the tropics and the savanna, and understanding them requires a different frame entirely. In winter, the Arctic is not merely cold. It is a comprehensive assault on the possibility of life as we normally understand it. Temperatures drop to -40, -50 degrees Celsius in some inland Arctic regions. The wind, when it comes, reduces effective temperatures further still, to levels at which exposed human flesh freezes in minutes. The sun disappears for months. The sea ice locks the liquid water away under a surface that can be several meters thick in some areas and dangerously thin in others. And yet the Arctic in winter is not empty. It is populated by animals that have solved the problem of this environment with solutions that are, in their own way, as extraordinary as anything the rainforest has produced. The Arctic fox weighs around 3 to 4 kilograms. It is a small animal by any standard, and it survives winter in the open Arctic, not in a burrow, not in hibernation, but active and hunting and maintaining a body temperature of around 38 degrees Celsius when the air around it is 80 degrees colder than that. The gap between its body temperature and the ambient temperature is maintained entirely by its fur and its physiology, and both are extraordinary. The fur of the Arctic fox is the most thermally efficient of any mammal measured. The ratio of insulation to weight is higher than in any other species. The individual hairs are specifically structured to trap air and create a layer of still insulation across the entire body surface. The blood circulation in the fox's paws uses a countercurrent heat exchange system that warms the blood flowing back from the cold paws before it re-enters the body core, so that the fox can walk on ice and snow without losing significant heat through its feet. The fox can curl into a ball and reduce its exposed surface area, and use its thick tail as a face covering, and in this position can endure temperatures of -70 degrees Celsius. The fox weighing 3 kilograms is generating heat from a metabolic system that would seem entirely inadequate for the challenge, and yet it is sufficient, because every aspect of the body that uses that heat has been tuned for minimal loss. The hunting challenge in the winter Arctic is extreme in a different way. The lemming, the Arctic fox's primary food source, does not disappear in winter. It continues to live and breed and move under the snow, in a subnivean world beneath the insulating white surface that maintains a relatively stable temperature close to 0 degrees, warmer than the screaming cold above it. The lemmings move through tunnels under the snow, eating cached plant material, generating heat, living in what is effectively a different thermal environment than the one the fox inhabits above. And the fox has developed a hunting technique for accessing this hidden world that is one of the most visually spectacular predator behaviors in the animal kingdom. The Arctic fox stands still on the snow surface, turning its head slowly, triangulating sound with ears that are precisely shaped and positioned for this purpose. The sound of a lemming moving under the snow, through 30 centimeters of compacted snowpack, sound that a human standing in the same spot would have absolutely no hope of detecting. The fox hears it. And then the fox launches vertically into the air, 2 meters up, and comes down headfirst through the snow like a dart, using the momentum of the fall to punch through the crust, and sometimes, with a frequency that represents genuine hunting success rather than lucky accident, it comes back up with a lemming in its jaws. A prey animal it could not see, could not smell at that moment because the snow was blocking the scent, located entirely by the sound of movement through a medium that most predators would consider an impenetrable barrier. The fox has turned a barrier into a tool. Now, let me take you somewhere that almost nobody thinks of as a survival battlefield, but which is, in the full biological sense, one of the most intense survival arenas on Earth. Let me take you into the human body. Not metaphorically, literally, because the systems that operate inside a human body in response to injury and threat are survival battles at a scale and complexity that rivals anything happening on the savanna or in the rainforest, and understanding them, even briefly, changes how you think about what survival means as a concept. When a pathogen, a bacterium or a virus or a fungal spore or a parasitic organism, enters the human body, it does not enter a passive environment. It enters a war zone. It enters a system that has been specifically shaped by 300 million years of vertebrate immune evolution to detect, contain, and destroy exactly this kind of threat. And the pathogen, which has its own evolutionary history, its own suite of adaptations, its own toolkit for evading detection and exploiting host resources, immediately begins implementing those adaptations against a defense system that has been specifically shaped by the continuous pressure of pathogens exactly like it. The innate immune system responds within minutes, not hours, not days, minutes, before any specific immune response has been mounted, before any antibody has been produced. The tissues around the infection site have recognized that something is wrong. They have recognized it because the pathogen, whatever it is, carries on its surface specific molecular signatures, patterns that are characteristic of bacteria or viruses or fungi but not of normal body cells, and the cells of the innate immune system are equipped with receptors specifically designed to recognize these signatures. The recognition triggers an immediate chemical alarm, a cascade of signaling molecules, cytokines and chemokines and interferons that spreads outward from the site of infection and summons the cavalry. The neutrophils arrive first. These are white blood cells that exist in enormous numbers in the bloodstream, hundreds of millions of them in circulation at any given moment, and they are essentially suicide soldiers. A neutrophil lives for only a few hours to a few days. Its existence is entirely oriented around finding pathogens and destroying them, using mechanisms that are so aggressive that they damage surrounding tissue if not carefully regulated. A neutrophil can engulf a bacterium, surround it completely, draw it inside itself, and kill it using a combination of digestive enzymes, reactive oxygen species, and antimicrobial proteins. Neutrophil can also, in a behavior that was only discovered relatively recently, and that continues to astonish immunologists, eject its own DNA in a web of chromatin fibers called a neutrophil extracellular trap, a net that physically ensnares bacteria and exposes them to the antimicrobial proteins embedded in the web. The neutrophil kills itself to make the weapon. It disembowels its own nucleus to create a trap for the thing it was born to fight. This is not simple. This is not primitive. This is one of the most sophisticated defense behaviors in the biological world, operating at a scale so small that it cannot be seen without an electron microscope, happening right now in every human body in the quiet, unremarked trench warfare of the immune system. And the pathogens are not passive in this. The pathogens that survive in human populations, the ones that have successfully infected enough hosts to maintain themselves as species, are the ones that have developed countermeasures to the immune response. Staphylococcus aureus, one of the most successful bacterial pathogens of human populations, has developed the ability to produce a protein that mimics a human signal, tricking the immune system into treating the bacterium as a friendly cell. It has developed the ability to hide inside macrophages, the large immune cells that are supposed to engulf and destroy bacteria, surviving in the very cell that was designed to kill it, and using the cell as a refuge from the antibiotics that are circulating in the surrounding tissue. It has developed mechanisms that allow it to form biofilms, dense communities of bacteria embedded in a self-produced polymer matrix that is extraordinarily resistant to antibiotics and to immune attack, transforming itself from individual vulnerable cells into a collective structure that is orders of magnitude harder to kill. This is coevolution at its most naked, the bacterium and the immune system, each shaped by the other's attacks and defenses over thousands of years of continuous conflict in the bodies of human beings. The bacterium's genome carries the record of every successful immune evasion that ever helped an ancestor survive long enough to reproduce. The human immune system carries the record of every pathogen that ever threatened a population and was defeated or at least contained. Every vaccination that works, every antibiotic that succeeds, every fever that breaks is a chapter in this history. Let us come back out. Let me take you to the ocean. The open ocean is the largest habitat on Earth and in some ways the most poorly understood, not the surface which we can see and which has been studied extensively. The deep ocean. The mesopelagic and bathypelagic zones, the twilight zone and the midnight zone where sunlight penetrates only partially or not at all, where the pressure increases by 1 atmosphere for every 10 meters of depth, where the temperature is constant and cold and the darkness is total. This is not an environment in which we would expect life to thrive. It is an environment in which we would, if we were reasoning from first principles, expect almost no life at all. Instead, it is the largest inhabited space on Earth by volume, and its inhabitants have solved the problem of living in this environment with adaptations that are so extreme that studying them feels less like biology and more like science fiction. The anglerfish is the image most people have when they think of deep-sea creatures: the bioluminescent lure dangling from the forehead, the enormous jaws, the grotesquely large eyes, and the body designed around the principle that prey is so rare in this environment that when you encounter it, under any circumstances and at any size, you cannot afford to let it escape. An anglerfish stomach can expand to accommodate prey larger than the fish itself. An anglerfish jaw can open wide enough to engulf animals twice its body size. An anglerfish will eat anything, because in the midnight zone, anything is a meal. But the most extraordinary thing about the anglerfish is not the lure or the jaws. It is the reproductive strategy of the deep-sea varieties, which is among the strangest things in biology. The males of certain deep-sea anglerfish species are tiny, orders of magnitude smaller than the females. And when a male finds a female, which is a profoundly rare event in the vast darkness of the deep ocean, he does not court her, he bites her, and then he does not let go. His body begins to fuse with hers at the point of attachment. His circulatory system merges with hers. His organs begin to atrophy, everything except the testes, which are the only thing the male is still needed for. His body is gradually absorbed into the female's body until he is not really a separate organism anymore. He is a reproductive appendage, carried through the ocean inside the female's body, kept alive by her blood, ready to release sperm when she releases eggs. This is survival mathematics taken to a logical extreme that seems to violate the normal categories of individual and collective, of self and other. The male anglerfish, in becoming part of the female, solves the problem of the deep ocean, the vast empty darkness where finding a mate again would be essentially impossible. He finds her once and he stays. He trades his individual existence for the certainty of reproductive success, and it works. It has been working in the deep ocean for a very long time. Let me take you to the grasslands of Central Asia, to a landscape that most people in the world have never seriously considered as a place at all, even though it covers millions of square kilometers and has shaped the history of human civilization more profoundly than almost any other environment on Earth. The steppe, the Eurasian steppe, stretches in an almost unbroken arc from Hungary in the west to Manchuria in the east, a belt of grassland wider at some points than the entire United States is tall, a landscape of extraordinary emptiness and extraordinary richness existing simultaneously, empty of trees largely except along the river valleys, empty of the kind of topographic complexity that gives most landscapes their visual drama. Rich in grass, in the deep black soil, the Chernozem that centuries of decaying grass roots have created, in the ungulates that evolved to exploit the grass, in the predators that evolved to exploit the ungulates, and in the humans who figured out sometime around 5,000 or 6,000 years ago that the way to live in this landscape was not to fight its vastness and emptiness but to move with it. The horse made the steppe human, not immediately, not simply. The domestication of the horse is one of the most consequential events in human history, and it happened here on this grassland, and it changed everything. Before the horse, the steppe was an obstacle. After the horse, it was a highway that connected the furthest eastern reaches of Asia to the westernmost edges of Europe in a single continuous passage that no geological barrier interrupted. The people who learned to use this highway, who learned to fight from horseback and to organize their society around the permanent mobility that horses made possible, became for several thousand years the most militarily and economically significant people in the world. They connected China to Persia to Rome. They moved ideas and diseases and technologies across a continent at speeds that would not be matched by any other transport system until the railroad. The survival challenge of the steppe is not the predator. The apex predators of the steppe, wolves and snow leopards at the edges and eagles overhead, are real threats to the livestock that steppe nomads depend on, but they are not the primary survival challenge. The primary survival challenge of the steppe is the steppe itself. The dzud, the Mongolian phenomenon that happens when a warm autumn is followed by a hard early winter, freezing the autumn rain into a layer of ice beneath the snow so that the livestock cannot paw through to the grass beneath it. A dzud can kill 70% of a herder's livestock in a single winter. A single dzud can end a family's entire economic existence in months. And then the spring comes and the grass comes up through the thawed earth, green and rich and impossibly abundant, and there is nothing left to graze it. Survival strategies that steppe nomadic cultures developed in response to this threat are fascinating precisely because they are social rather than individual. No single family, no single clan can manage the risk of the dzud alone. The solution that Mongolian and Kazakh and Tuvan and other steppe nomadic cultures developed is a web of reciprocal obligation so dense and so elaborately ritualized that it functions as a kind of insurance system distributed across the entire social network. When a family loses its herd to a dzud, the network of kin and allies and trade partners provides animals to restock. The family that receives this help carries an obligation, encoded in custom and ceremony and memory, to provide equivalent support when the time comes. Over generations, the network balances itself. No one family accumulates enough surplus to survive the worst DZUDs alone, but the network collectively manages a reserve that any member can draw on. This is not charity, it is not altruism in the naive sense. It is a rational response to a survival challenge that cannot be solved individually and requires collective infrastructure. The ceremonies that maintain these relationships, the elaborate hospitality protocols of Mongolian culture, the ritual slaughter of animals at specific occasions that are simultaneously religious events and redistributive economic events, the marriage alliances that extend the network across ever wider geographic areas, all of these are infrastructure. They are the organizational technology that makes survival possible in an environment that would kill an isolated individual with complete indifference. Let me take you to the ocean again, but differently this time. Let me take you to the tidal zone. The intertidal zone, the strip of coast that is covered by water at high tide and exposed to air at low tide, is subjected to greater environmental variation over a 24-hour period than almost any other habitat on Earth. Twice a day the ocean covers it. Twice a day the ocean retreats and leaves it exposed to air, to sun, to temperature extremes, to desiccation, to rain that can dilute the salt water in tide pools to near freshness in a heavy storm. The animals that live in the intertidal zone are not living in the ocean. They are not living on land. They are living in the catastrophic space between those two environments, subjected to the challenges of both and the stable conditions of neither. The limpet is perhaps the most successful intertidal animal, in the sense of having colonized the zone most thoroughly and survived in it for the longest evolutionary time. A limpet is a gastropod, a snail without the spiral shell, instead carrying a low conical shell that it presses against the rock surface with extraordinary force. The clamping force of a limpet per unit area of foot surface is greater than the grip of any known suction device of comparable size. It can resist wave forces that would displace objects many times its mass. And it can survive being exposed to air in full sun in summer temperatures by producing a mucus seal between its shell edge and the rock surface that prevents desiccation, reducing its body's water loss to nearly zero while it waits for the tide to return. But the limpet's survival strategy is more sophisticated than clinging hard and waiting. A limpet has a home scar, a specific spot on the rock surface, the exact shape of which matches the edge of its shell, worn into the rock by years of returning to exactly the same spot after each low-tide excursion. The limpet grazes during high tide, rasping algae from the rock surface with a structure called a radula that is, by weight, the strongest biological material ever measured. Stronger than spider silk, stronger than bone, because the teeth of the radula are mineralized with a form of iron oxide that is harder than almost anything else a biological organism has ever produced. It grazes and it moves, and then, as the tide retreats, it finds its way back to its home scar, millimeter by millimeter, following chemical trails and topographic cues in the rock surface, and settles back into the exact position where its shell fits precisely against the rock. The fit is so exact that the contact between shell and rock is essentially watertight. In its home position, the limpet is nearly impregnable. A herring gull landing on the exposed rock can lever off a limpet that has not yet clamped down. It cannot move one that has settled into its home scar and committed to holding. The limpet's radula, the anglerfish's lure, the Arctic fox's ear, the neutrophil's extracellular trap, the leafcutter ant's antibiotic bacteria, the impala's threat matrix, all of these are solutions to survival problems. All of them are the accumulated result of selection pressure acting on variation over time. All of them are, in the deepest sense, the record of a battle that never ends, because the environment never stops presenting challenges, and the organisms that survive are the ones that have, by whatever means, found responses that are adequate to those challenges. And here is the thing that I want to sit with for a moment before we go further. Because there is a tendency, when we talk about survival battles and predator and prey and evolutionary arms races and the ruthless logic of natural selection, to frame all of this as brutal, as evidence of nature's indifference. As a kind of theater of suffering that we observe from a comfortable remove, grateful that we have elevated ourselves, through technology and civilization and the insulated structures of modern life above all of this. Grateful that survival for us does not require the hypervigilance of the impala at the drinking hole, or the patience of the leopard in the fever tree, or the daily gamble of an Arctic fox in a landscape that could kill it in any unguarded hour. But this framing misses something important. It misses the fact that every solution we have looked at today, every adaptation and behavioral strategy and social system is also beautiful, not in spite of its violence or its ruthlessness or its cost, because of it. Because a thing that has been shaped by 50 million years of selection pressure to be exactly what it needs to be has a kind of perfection that design things almost never achieve. The limpet's shell fits its home scar exactly because any shell that did not fit exactly was a limpet that desiccated and died. The Arctic fox's ear is precisely the right shape to detect lemming movement through snow, because any fox with a less precisely shaped ear caught fewer lemmings and had fewer surviving pups. The impala's threat matrix is the size and complexity it is because any impala carrying a smaller or simpler threat matrix is a dead impala. Selection pressure is not cruel. It is precise. It is the most exacting engineer that the universe has access to, and it produces, over enough time, solutions of extraordinary elegance. Let me take you to a survival battle that operates at the longest time scales. Let me take you to the competition between trees. A forest is not a stable or peaceful community of plants coexisting in benign proximity. A forest is a war. It is a war fought in slow motion, in timescales that are invisible to any individual human observer, but a war nonetheless over the single resource that every plant in the forest needs above all others: light. The forest canopy is the front line of this war. The trees that reach it and hold it receive the sun and can grow and reproduce. The trees that fail to reach it grow in dim shade and may persist for decades as stunted understory plants, or may die, slowly, starved of the energy they need to maintain their own tissue. The strategies that trees have evolved for this competition are extraordinary in their variety and their sophistication. The fast-growing pioneer species, the trees that colonize a gap in the forest created by the fall of a mature tree, produce wood quickly and cheaply, lightweight wood that allows rapid vertical growth, deploying their investment in height as fast as possible to claim the light of the gap before it closes. They are not built to last. Their wood is soft and rot-prone, and they may live only a few decades. But in a gap, in a moment of opportunity, they can reach the light and reproduce before the slower-growing canopy species close the opening above them. The slow-growing hardwood species do the opposite. They invest their energy not in speed but in density. They build wood that is dense and hard and rot-resistant, wood that takes decades to reach the canopy but that once there will last for centuries. Their competitive strategy is not the sprint of the pioneer. It is the long game, the accumulation of structural capital that, in the end, shades out and outlasts the pioneers that arrived before them. The great hardwood trees of the temperate and tropical forests, the oaks and the beeches and the mahogany and the Brazil nut trees, are winning a competition that